My name is Noah Wolf.
My name is Lovejoy-Johnson.
And I'm Grant Sherrill.
And our project had two main goals. The first of these goals was to develop a hydrodynamical simulation that could potentially run in reasonable time on a personal computer. And so in order to do that, we used the particle in cell method described by Evans and Harlow. And what that involves is you divide your hydrodynamical simulation into two grids. The first is a grid coordinate system for all of your cells, which have properties of internal specific energy, and x and y component velocities and pressure, and another coordinate grid system for all of your particles. And then you divide your calculations into three phases. In the first phase, you use discretized versions of the Navier-Stokes equations to calculate new x and y component velocities, as well as new internal specific energies for each cell. In the second phase, you apply the changed x and y component velocities in order to move your particles. And what we did is we said if we had a particle in the corner of one cell, it would be potentially influenced by neighboring cells. So you draw a circle around that particle. You use Monte Carlo methods by dropping random points in that circle, figuring out the proportion of points in that circle that fall in different cells, and then weighting the velocities of those cells according to the proportion of points in that circle which fell in that cell. And then finally, in the third phase, what we do is we apply transport corrections to the energy, because particles can potentially move in and out of cells, and you want to account for the energy that they bring or take away from those cells. And then I think this leads us into the equation of state.
So we used an equation of state to find pressure values at various different time steps, because that really shows the evolution of our system over time. We used these changes in internal energy to find the pressures as the time increased. Now we looked to the van der Waals equation to find the equation of state. We ended up going with an ideal model as a decreased computational complexity.
For the second phase of our project, we decided to model a real-life weather system using our particle in the cell method. In order to do this, we picked a random point in the entire system. This point would be considered the center of our storm. The cell at this point would have the lowest density and the highest temperature. The pressure around this center point would slowly increase over time, while the temperature would decrease over time. As you see, the center point is highlighted in red. The pressure will be slowly decreasing outwards. In order to have this decrease, we use a multivariate normal distribution. This made it fairly random still, but it still allowed us to pick a center point and have it increase outwards without so much change. And using this, we were able to get a decent, accurate measurement of pressure and temperature, but it wasn't perfect. And we found that a lot of energy and other calculations were flawed due to this.
During our calculations, we created this system without any energy, and then we added in a lot of energy by using this pressure and this temperature. Because of this, a lot of energy was thrown into the system and it didn't really have anywhere to go. Along with this, the energy just kept adding up over time and eventually oscillated unbounded. This caused cells to bound off each other and eventually leave the system explosively.
So as you can see on the animation of particle motion shown for one of our simulation runs, you not only can see this unbounded oscillation in the values, but you actually see what looks like different shock fronts bounding off of each other. And we realized one potential cause of this is the fact that we do not have any viscosity in our system, and it's a perfect ideal gas. So, as Grant said, we put in energy to the system, there's a periodic boundary condition, and so it essentially continues to oscillate off itself as if it's an undamped oscillator that's driven. And so in order to explore that a little more, we looked at what we called the VEV, or velocity effective viscosity, where we went to our effective velocity calculations in phase 2 of the particle in the cell, and we applied a VEV coefficient, some unitless coefficient, to dampen that somewhat. We tested this with 10 values from 0.1 to 1, and we found the following graph, where we find an expected relationship in that the Maximum time steps our simulation reaches before the velocity passes some threshold of 10 to the 8 meters per second, which we felt was fairly significant for saying it's now growing without bound. So the maximum number of time steps the simulation runs before hitting that threshold does decrease as the viscosity coefficient increases because we are dampening it less, and so it more quickly reaches that threshold. However, the fact that there's not a clear trend line here, as well as the fact that we still reach that unbounded state, even at a dampening coefficient of 0.1 or 0.2, seems to indicate that there are likely better ways to handle this viscosity coming from the Navier-Stokes equations that are more in line with the actual physics happening. Another computational challenge we encountered was that even though we were able to use NumPy optimization and methods to significantly reduce computation time, in the end we were still unable to model realistic problems in terms of scale on a personal computer, such as the dimensions of our grid or the size of our cells, or even the number of particles. So one solution we came up to solve this was to use what we called superparticles, which were essentially very large particles that would account for many much smaller particles in reality, but reducing the number of computations we have to do.
And thank you for your time.
Yeah, thank you very much.
Thank you.